Hello, today I will be introducing how I discovered self-induction of Faraday's law to prove the inapplicability of the Lorentz force in relativistic electromagnetism. We are all familiar with these equations in this figure shown here. However, we have not been able to explain the difference between the up and down figures by using electric and magnetic fields. Therefore, today I will demonstrate how I was able to explain the difference between the two figures and use self-induction of Faraday's law to reveal why the Lorentz force in relativistic electromagnetism is inapplicable. In my presentation today, I will first clarify how electromagnetism is about the motion of electric charge, not mass. Next, explain why electric charges in Maxwell's equations must be distinguished. Then, in Faraday's law and Maxwell-Ampère's law, distinguish between an electric field and magnetic field to prove self-induction of Faraday's law. And lastly, explain the inapplicability of Lorentz force and the Minkowski force in relativistic electromagnetism by using self-induction of Faraday's law. Before I demonstrate how I discovered the self-induction of Faraday's law, I want to clarify that electromagnetism is used here to explain the motion of electric charge, not mass. There are three different velocities of an electric charge. First, when the velocity of an electric charge is zero, an electric field exists according to Gauss's law. Second, when the velocity of the charge is constant, current flows, which means the charge generates a magnetic field, according to Ampere's law, and an electric field also exists. Here, the definition of current is the rate of electric charge per unit time. However, the more accurate definition of current is that the charge carrier, Q0, does not change over time, but the charge carrier Q0 in matter moves with a constant mean speed. Lastly, when the charge oscillates, there are two mechanisms. One is Faraday's law and the mutual induction of Henry's law. Both laws show that an oscillating magnetic field generates an electromotive force, which is induced by another electric charge. The other mechanism is Maxwell-Ampere's law and the self-induction of Henry's law. Both laws show that an electric charge oscillates, and Maxwell-Ampere's law shows that only an oscillating charge emits an electromagnetic wave composed of electric and magnetic fields. So, I discovered that Faraday's law needs two electric charges and Maxwell-Ampere's law needs only one electric charge. In order to accurately mathematically derive wave equations from Maxwell's differential equations, we must use the subscript according to the electric charges to distinguish an electric and magnetic field in Maxwell's equations. This figure shows that there are two different magnetic fields. Because Faraday's law requires two different charges, thus, we cannot derive wave equations with Maxwell's differential equations shown here. However, because this figure shows that there is an electric field and a magnetic field generated by one oscillating charge in Maxwell-Ampere's law, we can obtain self-induction of Faraday's law. We can also derive wave equations with Maxwell's modified differential equations, including self-induction of Faraday's law. From our discovery of self-induction of Faraday's law, we now know moving forward that an electric and magnetic field must be distinguished according to its electric charges. When we apply that knowledge to the Lorentz and Minkowski forces, we can examine whether or not the forces are applicable to relativistic electromagnetism with the mathematical expressions of the Minkowski and Lorentz forces. As shown in this figure, because charge QE at stationary state generating an electric field is equal to charge QE moving at uniform speed generating a magnetic field, the Lorentz force cannot distinguish between an electric field and magnetic field generated by each electric charge. As a result, charge QE generating an electric field must be distinguished from charge QE generating a magnetic field, and we must clearly define the electromagnetic force between two distinguished electric charges. An electric force is generated only when one of the two charges is stationary. On the contrary, a magnetic force is generated only when both charges move simultaneously. The magnetic force is generated as either attraction or repulsion depending on the magnetic fields generated between the poles and according to the direction of the two moving charges. Furthermore, because charge Q0 is moving at constant velocity, it also generates a magnetic field according to Ampere's law. Therefore, the Lorentz force must have three different charges for the perspective of matter, as you can see in this equation. We are also familiar with these equations shown here. But these equations require four different types of matter because the accelerating matter with mass m and electric charge q is different from the uniformly moving matter with mass m0 and electric charge q0. From these equations, we can find several physical problems. First, the rate of change of linear momentum is based on the perspective of the mass of matter rather than that of an electric charge. But there is no physical interaction between mass and an electric field and magnetic field. Second, if the amount of charge q on mass m is defined, since the terms of these equations are already composed of the electric forces between charges QE and Q0 and the magnetic forces between QB and Q0, then the forces of the three additional cases, the electric force between the charge Q and electric field of charge QE, the magnetic force between Q and Q0, and the magnetic force between charge Q and magnetic field of charge QB can also exist. Next, to use the Lorentz force, matter, quantified with charge Q and mass m, must be identical to matter, quantified with charge Q0 and mass m0. However, because the velocity of the charge q is already defined as v0, the mass m cannot be accelerated with translational motion. The motion of mass m can only be uniform circular motion to convert the non-zero acceleration into constant speed v0. Lastly, v0 in the Lorentz factor within the Minkowski force can only be translational velocity, which means that the rate of linear momentum within the Lorentz force and Minkowski force is no longer applicable. Thus, we can conclude with two key points about the Lorentz force. First, because the Lorentz force in a fixed inertial system requires three charges of different speeds, the observer in a moving inertial system must physically distinguish between the charges that generate an electric field and the charges that generate a magnetic field. Second, for the three charges of the Lorentz force, two of the three charges generate a magnetic field in accordance with Ampere's law, and all three charges generate an electric field in accordance with Gauss's law. Therefore, because the well-known Lorentz force cannot distinguish between an electric field and magnetic field generated by each electric charge, relativistic electromagnetism of the Minkowski force is useless.
If you'd like to further discuss, then please visit this website and leave your comment to get the $1 million prize. Thank you very much for your time.